regression recap and related. We did that in the logistic regression. We are through that as well. Multi-level analysis, that's the next topic that we'll go through. And well, there are two reasons basically why you would want to digress from the standard multiple regression. Here you see the two reasons that we're covering here. First, your Y is binary, then you get your logistic regression. And another issue that we have that will not allow us to run our standard multiple regressions is what's called repeated measures or clustered data. More in a minute about exactly what that is, but that will cause us to have to go with multi-level regression. Okay, so let's see. What is that? We have a couple of data sets that I'd like to go through. Several of these we will have in the wikis as well, and some of these we'll actually look at in some detail, but it's good to get a feel for the kind of clustered data that we have here. This is one standard example that I'd like to use because this is typically where it came from actually. If we do research in school classes, and we have students within classes, and if we have, for instance, a measurement on one predictor variable here, introversion, how introvert you are, might be a predictor for how well you do in school. We could check if that's actually true. So that would be on the x-axis. Typically, here it now says something about school. Disregard that for a minute, but we're trying to figure out if being an introvert is doing damage to your grade, or is perhaps even a good thing for your grade. And if we have lots and lots of data from lots of students in different kinds of classes, you can very well imagine that if you have measurements from persons in the same class, that somehow they are related. If I measure something on you, and let's say the extent to which you score has something to do with the rest of the class or the teacher, then if I measure something on somebody else in the same class, this is not really a new case because it's coming from the same cluster of data. And that will turn out to be an issue. Well, let's take this one here. We have data that's called fastfood.dta, where we get as the target variable the grade that employees from a burger restaurant or a chicken restaurant give to their managers. So all the employees in one of these fast food restaurants have been asked, okay, give a grade to your actual manager. And there too, well, there are all kinds of reasons why if I sample somebody, one person from one fast food restaurant who is saying something about one particular manager, well, in all likelihood, if you sample somebody else, well, what they typically have in common is that manager and the whole surrounding and the atmosphere in that restaurant. So this is not an independent observation. Again, we have data that are clustered, and we'll see in a minute why that is an issue. Or here, I'm trying to figure out, is there an effect of the size in square meters of a house on the asking price of a house? Well, normally you would think, yes, obviously, the larger the house is, the more expensive it will be, and in all likelihood that will be the case. But it can very well be that if I sample two houses that are very near each other, then what they have in common is the neighborhood in which they are. And it's reasonable to think that, well, the neighborhood by and of itself will also have an effect. So this is not an independent sample, and that is an issue. Again, clustered data here. And here another one that you have been part of yourself, I think. With your phone, you can measure your heart rate increase, and you do that typically, well, actually 3 times. Once the base rate, so without you doing anything, and then twice, once when you remember a case where you were angry, and once where you remember a case where you were happy, and then we measure heart rate once again. Well, you have 3 measurements on you. If you would treat that as 3 separate measurements, or if you would look at the increase, so we compare with the base, how much do you increase your heart rate depending on these 2 conditions, then you could say I have 2 measurements on every person, and I have to take into account that both of these come from you. If I would do all measurements only on you, that would be not a good idea. I have to take that into account. Our data are clustered in this case within persons. And in psychology, this is typically what we have. You have people in a lab and you want to somehow vary a couple of conditions on them, perhaps even all the conditions. So we look at you and, once we look at you with the light out and then with the light on in a certain color and the light on in another color and still another color with higher intensity. And now we compare how you do across these different conditions. Now we have 4 measurements on you and we have to take that into account. This is the data set that you'll have to work with in the assignment, so it's perhaps a good idea to go through that in some detail as well. This is data from Interpolis. What they measure from different people, from all their clients, is prevention behaviors. And yeah, behaviors is perhaps not exactly the good word. The stuff that people buy, for instance, a fire blanket. So the only thing you have to do there is you buy it and then you have it in your house. So this is a prevention measure that you can have or not. Or you own an alarm. That would be one thing that they would measure. But they also measure, do you clean your gutters? If you do not, you are much more likely to get water damage in your house, and that's a bad thing for Interpolis. So this is also a prevention behavior. So in a way, this is more of a behavior than that. You have to buy that once and then you're done. Or this, closing your door when you leave the house, or actually not closing, locking your door when you leave the house is also a prevention behavior. They measure this for, I don't exactly remember, let's say 9 or 10 of these different behaviors. So you get 9 or 10 rows in your data, all of which represent the same person. And what you could try to figure out, for instance, if the perceived effectivity of the measure is an influence on how likely it is that people actually do this. So if you don't believe that it makes much sense to lock your doors, because you know, if there's a thief there, they will open it anyhow, then perhaps you're less likely to actually do this. And to see to what extent this effect is there, you can use this data, but every 10 rows that you have is from the same person, and you have to take that into account. Okay, any questions up to now as to how, what these data sets typically look like? More than a single row from the same cluster, and that could be data points as here, where let's say the lowest level behaviors are prevention behaviors, and the cluster is a person, or it could be that we have more persons within a class. So it need not be persons on the highest level, could be anything, in fact. Let's see, yeah, if at some point later on you figure out, okay, I'm going to need this somehow because I see that I have these cluster of data, and now what do I do? If you try to find this online, it's not that obvious. If you look for multiple regression, you get a lot, and this is called multiple regression everywhere. If you look for this, then all these different labels here refer to the same thing. And this is because in different disciplines, in sociology, in psychology, in educational science, or even in physics, they do this, but it's called differently. What we will use here is typically mixed models, like that, or multi-level models, but all the other ones here are basically variance or exactly the same thing. So that might cause some confusion if you later try to figure that out. Actually, the thing that we're going to look at today is called the variance component model. Anyhow, lots of labels for basically the same thing. Okay, so here you see a couple of these examples. This is your typical HDI example. We have measurements within persons. Here on this row, all the lower levels. This is the fast food example. We have employees within stores or within restaurants. Here we have prevention measures within persons. That's the data that you're going to use as of next week. It could be pupils within classes or firms within sectors. Anything where you could feel that you have clustered data might be an issue. There is no need to think that the persons need to be at either level. They are here at level 2, and there as well, and there at level 1. Okay, two things that we're going to go through today, the two main messages actually for these kinds of data. First, well, the problem with just running a multiple regression as if nothing had happened would be that your confidence intervals in all likelihood will be too tight. So normally you get an estimate for a predictor, you get a confidence interval around that estimate, and that confidence interval will be tighter actually than it is supposed to be. And in a minute I'll talk a little bit more about why that is. And then the other thing that you can do with these kind of data, and that you also should do because it helps you test more of what's going on, is you can try to find effects within the clusters and between the clusters. And both of these we're going to go through today to see what exactly that is. So first a toy example here. We're trying to figure out are boys smarter than girls, and we're sampling 5 boys and 5 girls, and we are going to give them an IQ test. In fact, not just a single IQ test, we measure their IQ 100 times, and the data will look like this. This is subject number 1, On measurement 1, the IQ was measured as 126. This is the first measurement, and this was a girl. This continues all the way up to there, 100 lines in the data, still the same person. Measurement 100 is 120. It's still a girl, obviously, and now the next 100 lines are from a boy with a obviously lower IQ level here, and so on. So our data is now what we have, 10 boys and girls times 100. So we have 1,000 rows in our data, but in principle they are only from 10 different persons. You also see the standard problem here. Well, if we do just that, trying to predict IQ from whether or not you are a boy, or run a t-test, doesn't really matter so much. Yeah, one of the assumptions there is that all these separate cases that you have count equally, for an equal amount of information, so to speak, and they typically don't. If I measure your IQ once, twice, 3 times, 4 times, okay, there is some measurement error perhaps in there. Maybe you had a good or a bad day, but as soon as I reach, let's say, measurement 25, number 26, 27, 28 is not going to deliver much more information. I've got you nailed quite well, and there is no extra information in there anymore. So I'm more or less, let's say, supposing that I have 1,000 separate cases here, but I don't. I really have less. I do not know exactly how much less, because I do not know how much noise there is in these 100 values, but I do know that the 1,000 that I would calculate with if I run a regression, that's way too large, and perhaps 10 would be too small. I have 10 persons actually delivering me these data, but it has to be, let's say the true n has to be somewhere between 10 and 1,000. If you're prone to more the formulas and the numbers, here you see actually how wide the confidence interval is. You see a formula here for the width of the confidence interval around the estimate. And you see the n in there, and this is the n. Stata doesn't know which n to use, and if you don't tell Stata anything, it will simply take the number of rows that you have, and that's it. Okay, so measurements are going to be too precise. And there, this is actually the data from Daniel, but then arranged in a different way than he did it. He had, I think, the data in 1 row per person. Here I've put it in 2 rows per person. This is the subject with ID number 1. Here we see, well, let's look at the last column first. This is not the happy manipulation, so this was when you were angry. And this is the happy manipulation, so 2 rows for you. You were in the condition here where you did the anger first and then the happiness. This is what your baseline was. And here, this person had an increase of 4 for the anger manipulation and a decrease of 3 actually for the happy manipulation. So here too, if we're trying to figure out, okay, is there an effect here of the happy manipulation in this case? Well, I have to realize here that every 2 lines is from the same person, and that we're measuring not, I don't know exactly how many that we had here, but the total number of rows, but in fact only half of the people are delivering us these kinds of data. I don't remember if I put it online already, but I think at least after tonight there will be a wiki also with the actual data to play around with. Okay, so this is what you get if you just run a regression here, and this is typically where it actually might go wrong, because here you see, if I look at the happy manipulation over there, that this effect is, well, it's significant, but not really, really strong. So in all likelihood here, if I would correct for the fact that we have 2 lines per person, it might very well be that then it is no longer significant. Could be. And here it says 136, whereas I know that the number of people that we had was actually only half of that. Okay, that's that. Okay, so first thing is, this is what goes wrong if you close your eyes and just run your regression. So first I have to let that sink in. So if that's not clear, let me know now. Everybody fine with that? Sure? All right. Okay, so let's suppose that this is one of these data sets that we have. And we can think about 2 examples here. One would be the x-axis over there is how introvert you are. Let's say that this is measured on a scale from 5 to 33, whatever that may represent. And this is the student grade, and student grade here is now running from 40 to 180, but doesn't matter so much. And if you look at the data here, you see a negative trend. This is the regression line that fits best, suggesting, well, the more introvert you are, the lower your grades. Okay? So you might think, okay, we're done. There is a negative effect here. That's it. Or if you look at this, this could be age, the age of the employee rating the manager in a certain fast food restaurant. And this would suggest, okay, the older an employee is, the lower score they give to their own manager. Okay? Well, the trend is there, but if in this case you would have realized that these data are clustered, it might very well have been like this. In fact, these data points here are the same. Now I color-coded the ones who are belonging together. So these light green ones are from one class, let's say, and the blue ones are from one class. So actually, within classes, the effect is positive. It's in the other direction. It's only that between classes, the effect is negative, like this. So actually what you would see here is, if we take being introvert and your student grade again, within a class, the more introvert you are, the higher you score. It's just that between classes, there are differences that are sloping downward. And that means, and this is slightly different, and you have to get your head around it, in classes with more introverts, grades are lower. Okay, and these two arguments are not the same, or in fact really different. In fact, in this case, empirically, you also get one's positive and one's negative. That need not be. But it can be very well the case. And substantially, it really means something different. Okay, these sloping upward, this is really saying, okay, within a class or within a group as we are here, the ones who score high on introversion are the ones with the higher grades. And this one is different. In classes with a lot of introverts, grades are lower. And you could have different reasons for that as well. So one reason would be, in classes with lots of introverts, nobody asks a question. Okay, and if nobody asks a question, then the group as a whole knows less, and your grades are lower. That could be one argument that is consistent with these data. And the increase in line could be, well, if you're an introvert, I don't know, you listen better, and given that you listen better, you score higher grades. Two different arguments, testable with basically the same predictor here, as long as you realize that the data are clustered. Now, same for age. Let's suppose that this is age, and this is, what was that again? The grade that they give to their manager. This would mean within a fast food restaurant, the older ones give higher grades to their manager. And across fast food restaurants, restaurants with a lot of old employees, on average, give lower grades. Substantially really different. And the fact that it is clustered data makes it possible, actually, and reasonably easily, as we will see, to disentangle between the two. Okay, let's see. Let's try that argument here. We have asking price and size in square meters, and we have data clustered in neighborhoods. So normally, well, what would we have to disentangle the two? One would be if I have within a neighborhood the houses that are bigger, then the bigger houses within a neighborhood are more expensive. That makes sense to me, would be a positive effect. And the effect between the clusters could be negative, could also be positive, but could be totally different in any case. The argument would be if you have whole neighborhoods with bigger houses, then you have, well, higher or lower prices than in neighborhoods with less bigger houses. Argument is really different. And the key difference is that, perhaps the easier way to think about it is, here, if this would be introversion, the within class effect is about the introversion of you. The between class effect can very well be about the introversion of others. So in classes with a lot of introverts, even an extrovert would get lower grades. Okay, so it's not about the property that you have yourself, but it is about the property of the cluster around you. Okay. Can we? Let's try that here too. So disentangle the within and between classes effect. Let's see, we have prevention behaviors there, and we have perceived effectivity. Okay, so within persons, if you ask me for 10 of these things, which of these I find most effective. A positive effect there would mean the ones that I find most effective, I am more likely to have or to do. The other between cluster effect would be, let's say that it's also positive, the ones who in general think that things, the whole set of 10 things, are more effective. Let's suppose that I think that everything I find very effective, then I'm more likely to have more of the whole set. Slightly different argument here, but again, between clusters and within clusters, there's a difference. And we'll try to disentangle that. Okay, let's do this. Yeah, and now the partitioning out of these two things. There is, if I have any kind of target variable that I want to explain, with any kind of predictor variable, if the stuff is clustered, I can try to partial out the variance at the cluster level and the variance at the individual level. And let's take one toy example. It's relatively easy. We have 4 cases here, cases from 2 schools. The green school, number 1, with 2 measurements there, an exam score of a 3 and a 2, let's say that's good, and a -1 and a -4 on school number 2. Okay, so only 4 data points, nothing special. The overall mean is designed here to be 0, which makes matters a bit easier. So on average, the 4 students here score a 0. And even if you just look at this, then you already see that, well, it looks like the difference here that you see in these 4 data points is due more to the schools than it is to the pupils. Now let's see if we can make that happen in terms of numbers as well. Okay, first we calculate the total variance. What was the total variance? Let's see. We look at the mean there, we look at how far they are away from the mean, and we square those numbers. So here 3 squared is 9, 2 squared is 4, -1 squared is 1, and -4 squared is 16. And I divide that by the 4 cases that I have, giving me a 7.5. So this is a measure for the total variance that's in the data. Now, where is that variance? Let's see. I now look at the variance of the school means around the overall mean. School mean for the green one is 2.5. School mean for the red one is -2.5. The rest is exactly the same. I look at the variance of the schools here. Well, 2.5 squared, that's this number, -2.5 squared, and now I have only 2 terms here, giving me a 6.25. So the total variance that I had was 7.5, and 6.25 of that is at the level of the schools. And perhaps there is no surprise if I now look at the variance of the pupil scores around their school's mean. A bit more work. This is the school mean for the green one. This is the school mean for the red one. And let's consider these separately. 3 minus 2.5 squared, 2 minus 2.5 squared, that's that one, plus -1 minus -2.5 squared, and so on, divided by the form terms that I have, 1.25. And if you remember, oh, wrong direction. The 7.5 that we started with is the total variance, 6.25 at the school level, 1.25 at the pupil level, or 82% versus 18%. So you can get an estimate here about the extent to which, let's say the explanation of what's going on resides at the clustered level or at the individual level. So here, if 82% of the total variation is attributable to school level factors, it would be a good idea to measure school level things. You know, what kind of policy do they have? How good are their teachers, or anything that is related to the school? And not so much, how much is a single pupil studying, or all kinds of other characteristics that belong to the individual here. Because only 18% of the total variance resides there. So if you would know this up front, then it would be a good idea to look for school level differences in your measurement. And that's usually very useful to know, because if you have survey data, then typically what you have is a huge list of potential questions that you need to bring back, otherwise it becomes too long. Nobody will be willing to fill it out. And if you know that it's all at the school level, then it's way better to look for questions at the school level instead of questions at the individual level. Okay. Let's see. I just answered this question. So why would this be important? This will tell you, okay, from all the predictor variables that I would like to have, I think it's a good idea to look at, well, either the one at the cluster level in this example, or if it would have been the other way around, so 82% at the individual level, ask for individual level variables. Okay, let's say, yeah, we did this already. So two things, no standard regression, because we'll get significant effects, or might get significant effects where they really are not. Effects between and within clusters, that will help, because you can see or test different kinds of explanations with the same data. And we need to partial out somehow how much of the variance is at these different levels. That'll help a little bit in trying to find the predictor variables that work for us. Okay. One solution that you shouldn't do, and I see it every once in a while, is, okay, I see that I have clustered data. So one thing that I can do is, and that gives me some trouble because I have more rows of data per cluster, I could simply average out all the data per cluster. So if I have multiple measurements per person, I simply average out, and then instead of the 10 cases per person that I have just one. That will actually solve the problem in the sense that there is now no dependency anymore between the rows, but it also decreases your data by a factor of, depending on how many rows per person you have. If I have 10 rows of data per person, now my data set is 10 times as small as it was before. And besides, all the individual level differences I can no longer test because I just aggregated all of that out. So even though you get rid of the actual, let's say, statistical problem, it's not a good idea to do this. So what can we do here? Now we get into the nitty-gritty part. Hang on. This is what we normally have. This is your standard regression. No light. There. Your standard regression model. Usually I don't talk too much about this part, but now I need to. There's an epsilon there, a random term. That thing needed to be normal, and it also needed to be independently distributed with a covariance matrix sigma square I. Okay, well, let's focus only on the fact that these residuals should not correlate. And if you have clustered data, these residuals do correlate. Think back about the example where I measure your IQ 100 times. If I run a model there and I know that for your first measurement of IQ, my model is too high, if you get positive residual, then in all likelihood my model will be too high for all your cases. So in that sense, knowing the first residual would tell me something about the second and the third and the fourth, and this is not allowed. So here we see, let's say, statistically exactly what's going on here that is not working. These should be independent, and they are not. Okay, now let's try to get rid of that. One way to get rid of it is to do this. I have several clusters. Now let's think back at these, let's say the class data where we had positive sloping classes and one downward sloping line through that set of lines per class. So actually, if you look at these different classes, what they have is a different intercept. They start at different points on the y-axis. So one way to solve this would be, okay, I give every class their own intercept. I add a dummy for class number 1. Class number 1 was here, so that will be that intercept over there. Class number 2 was there, so that is another intercept over there. And then I should be fine. And in principle, this is a solution. So here I'm adding dummies, D1 through Dj, for all the clusters that I have minus 1. So if I have, well, how much do we have here? Let's say 35 people here, and I have multiple measurements on you. I could add a person dummy for all but one of you. So I add 34 dummies to my prediction, and that would hopefully solve the whole issue. In principle, this is fine, and this will actually solve the problem. And the only trouble that you get here is that, yeah, very often you need to include a big bucket of dummies for that, and that may cause that the model itself will not be very convenient and anymore to estimate. So if I have, let's say, 2 measurements per person, and if I have to add a dummy for every person, this is giving me a model that, by and large, has half as much predictor variables as I have cases in my data. I don't want that. So this is one way out of it, but not very often tried. And later on we will see why this is not very convenient anyhow. That is because the way around it that we will find is relatively easy, actually. But in principle, this you could do. Dummies for every group, and you estimate the whole model, and you're good to go. However, we can try to come up with sort of a shorthand for that. if I estimate all these dummies here, let's say that there are 50 or so, I could try to look at that and look at these different dummies over here and the coefficients that I estimate. And let's say I get, you know, a 2 and a 4 and a 6 and an 11 and a 22. So they are somewhere between here and there, these different dummy coefficients. And I could say, well, perhaps they look like this, sort of normal. And if they do, I could summarize them by, okay, this is about this midpoint over here, plus or minus some noise. And that is what I actually do there. I'm saying, well, look at where the distribution of all these coefficients would be. I'm hoping that the distribution looks like this. And let's say that the mean of these coefficients is 7. Okay, first I can get rid of that 7. I put that 7 in the C0 over there. That's simply a constant, so I now shift the whole thing back to 0. So now basically what I'm saying is, okay, that extra 7, I put that in the constant over there, and I have some noise around 0 left. There. Noise varying with, and now not I, but J, with the clusters that I have. So for every cluster I have a bit of noise. There are a couple of assumptions that I need here. I was assuming here that all the noise, or that these things look like that, normal. Otherwise I cannot do any calculations. And I'm also assuming that the noise there is not correlated to the noise there. Okay, let's not bother about that for now. What this will help us do is, first, this drastically reduces the number of estimates that you need to take here, because this is now only one thing, whereas I had, well, as many dummies as I had clusters over there. And I've reduced that now to just one single thing to estimate, which is way more efficient if the assumptions are working. Okay, so that is the way out of the cluster problem. And if I have something like, you know, these different things with one downward sloping line, fine, I can solve that now, and I can solve it very efficiently if this will actually work. I'll show you in a minute how that goes. Now the second thing, that cluster part and a random part then is, well, divided by, there is a randomness there, the delta J, and there is randomness there, the original one, that's epsilon I. If you remember back the green and red school example, we did stuff like schools around their mean and individuals around their school mean. Well, this is the one and that is the other. And in a minute, what you'll get back from Stata is an estimate of the variance that resides there and the variance that resides there. And we will know, okay, data are clustered, fine. How much of the variance resides at that clustered level? Okay, then don't try to do both. So you might think, yeah, let's add all those dummies, let's see what happens, and then even still run my multi-level model. That you shouldn't do. You should do either one. Okay, so for the fast food data, how do we do this? Here you see an actual example. You need to tell Stata two things. First, you need to tell Stata, okay, if there are clusters in your data, where are they? There must be a variable in your data that represents the cluster. And in the fast food data, this is this one, xt set. The set is for define your cluster level, and this variable is called restaurant. Okay, so now Stata knows, apparently that's the cluster level. And now you simply run your regression, and the only thing that's different is instead of regress, I type xt regress. The xt is representative for the multi-level modeling. I do not know exactly what the abbreviation is standing for. And the first thing you do if you run something like this is you run the empty model. So the only thing that you have here is the target variable, in this case grade, the grade that they give to their manager. And this you get back. A lot that you need not bother too much about. For instance, okay, 803 cases in 145 groups. So apparently here I have 145 restaurants, each with, well, on average 5.5 employees. At minimum 3, at most 8. Okay, and in the end, what you get back here is two things that are of interest: a sigma u and the sigma e. Actually, the u belongs to the delta and the e belongs to the epsilon. And that one is the more important one of the three, because this is calculated as, and you can see that here, this one squared over this one squared plus that one squared. This is because these are variances, you need to square them. And that rho value over there says something about how large that sigma u is compared to that sigma e. This rho value is representing how much of the variance is at the cluster level. So in this case, we get a rho of 0.10 or 10%. So in this case, 10% of the variance in this restaurant example resides at the level of the restaurant. Or stated differently, most of the variance resides at the level of the individual. If I want to get decent predictors here, it's much more likely that I find them by measuring something that is a characteristic of the employee, not of the restaurant. Also, if you would have found 0 here, or something very, very close to 0, that would be suggestive of apparently there is no variance at the cluster level. So what I was worried about, that there is clustering at the restaurant level here, apparently that's not the case. So even though I thought, well, perhaps I will run a multi-level regression here, apparently the problem wasn't that problematic at all. Because if I look at the data, then I see, yeah, there is hardly any variance at the cluster level. And you could, in principle, get back to standard regression. Of course, the question then becomes, well, at which point should I start to worry about this number? The standard rule of thumb is if it's, let's say, 10%, yeah, this is certainly a threshold where you would say if it's above that, then make sure to run multi-level regression. Below, okay, there is some hand waving involved. What I normally stick to myself is, as long as my model is running fine, and if you have small data sets, that will nearly always be the case, I keep running the multi-level. You know, doesn't make much of a difference. It's a bit slower. The only thing that could happen is if you have a really big data set, it might be that this way of calculating is way slower than standard regression, and I might switch to standard regression, but normally I wouldn't. Typical, yeah, it's hard to say what typical values here are, but in data sets where you have clustering, typically you will see anything, let's say, between 0.10 or 0.5 or so. That will usually happen in these kinds of data sets. Way higher is not very likely. Way smaller is very possible. Okay, one other reason why it's good to stick to this kind of multi-level regression, even if there is a relatively low number there. Well, this is saying from all the variance that there is, 10% at the cluster level, 90% at the individual level. If I now start adding individual level variables, then some of the variance that I have over here is explained away if I have good variables. So this part is becoming smaller, and then relatively speaking, the cluster part is becoming larger. So if I would then rerun the model again, it could very well be that now, given that I have these individual level variables in there, now I understand that part better, and what is left is indeed variance at the cluster level. So it might very well be that this goes up as soon as I add individual level variables. And to be able to see that, it's good to stick to that as long as you can. Okay, questions about this part? Because all this is new and cannot be that this is all clear from the beginning. Who dares to admit it? All easy?
The last part about adding those
Yeah, and perhaps it's easier to start the other way around. If I know that 10% of the variance is at the restaurant level, in this example, if I start adding restaurant level variables, such as is this a burger restaurant or a chicken restaurant? Is it a Kentucky Fried Chicken or something else? I don't know. Are they located in the south of the United States or not? So all things that are related to the restaurants and not to the people who work there. Then I could expect, perhaps, that from that 10% of variance that I have, that I'm explaining away a little bit. So I had 10% of that variance, but given that I include those variables, it's getting smaller. So if I do that, then I would rerun the whole thing again, now with these variables behind it as predictor variables, and that number would go down, because I'm explaining away that part. Actually, and I'm starting with that one because it's in a way a bit more complicated for the other ones on the individual level, because if I add an individual level variable, I automatically add something at the level of the aggregate. And this is because, if I look at the means of the individual thing across the clusters, that also varies. So, but forget that for a minute. It works the other way around in principle as well. If I have lots of these individual level variables and I add them, let's say I have really good ones, I explain them all away, or almost all. Yeah, now all the variance that I have left is at the cluster level, and that number will be really high. So even if you see a value there that's relatively low, as soon as you start adding variables, it might go up. And well, I started first getting the data in, all the standard stuff, use fast foods. I have a look at the data, and well, I don't want to use too much time over that, but normally you do want to spend some time trying to have a look at the data, see what you have. So restaurants, you have counts from 1 to 145, so in all likelihood 145 restaurants, even though you do not know exactly if all numbers are represented here. We have burger versus chicken restaurants, whether or not the restaurant is in the south, the manager is male, the total number of workers in the restaurant income, the age of the employee who gives the rating of the manager, whether or not the employee has filed a complaint at some point against the manager, how long a person has been on the job, and whether or not the person who is doing the rating is male or not. Okay, so that's what's in there. Then normally I would simply tab all the variables and double check if all these values make sense. I will skip that at this point, but this is normally what you should do if you get some data. And I'm looking for any kind of missings that we might have. And you can also see from the summarize command already, all of these have 803 observations, so in all likelihood you won't find any, but if you have data where you do have missings, it's useful to have this missing values table summary. And then you would see here as well that this is okay. Here, just to get a bit of a feel for what the target variable looks like, that grade variable, I ask for a histogram here. And it looks like this. So, well, you might think looks pretty normal, which is in principle nice because that makes it usually easier to model it away. But, well, if we do the actual testing here, we see that in fact it's not normally distributed. Not necessarily a bad thing, only the residuals need to be normal, but I just checked to see what it looked like. So let's see. Then I would look at the data and perhaps normally I would think here, well, it makes a difference perhaps if the employee who is rating the manager is the same sex. So if manager and employee, for instance, are both male, I might want to add that as a predictor. Here I didn't, but in principle you could. And this is our standard regression material. Here I just run regression with age and regression with a separate dummy for each restaurant. So let's see what would happen there. Okay, first of all, well, no, let's do the regression with age first. We have that there. Okay, here we see negative effect of age. So older employees give lower grades on average, but this is without that within and between cluster story. 803 cases, so that's okay. And now separate dummies per restaurant with age included. So now I'm taking care of the fact that several of these dummies have, several of these restaurants have different intercepts. And you typically see, well, first of all, that it's a big mess, see, because now you get all these separate estimates for each and every restaurant separately. And still, where is it? An effect of age that is negative. It was, let's see, minus 0.12. Here, minus 0.15. So in that sense, it doesn't matter so much here. And it gives you now, well, loosely speaking, I think 140 or so variables that you are, estimates that you are getting here for 803 cases that you have, which is quite a lot. So I don't like this so much. And any normal regression now would continue. Okay, I have grade and I have different restaurant characteristics, burger restaurant, chicken restaurant, and so on. Now let's just run this. Well, perhaps get that histogram out. Otherwise it's in my face all the time. And here we see it, our standard regression table. R squared of 0.43, adjusted R squared also 0.43, loosely speaking. Some of these are significant, some are not. So let's take a couple. Chicken restaurants, positive coefficient. So if the restaurant is a chicken restaurant, their managers get graded higher, apparently. If it's in the south, on average, they also get graded higher, 0.3 extra. So, you know, all of that you can go through and see what works and what doesn't. But none of that is taking into account that actually the data here is multi-level, and this is the first bit that we already saw in the slides. This is the first part where first you define the cluster level here, restaurant, and then you run your empty model, and this one is new. Let me see what that looks like. So here you once again have that 10% of clustering at, of variance at the cluster level. And you might want to test here, is that 10% significantly different from 0? And you don't get it, there is nothing behind it over here. And if you want that, you can actually test it, xt test 0. And then you get a test of that. And equality with 0 is actually rejected. Could the guys on the phone in the back do something else, please? For instance, have a look here, given that you're here anyhow. Okay, so now we see the row of, what was it, 10%? And let's try a couple of additional analyses here. I'm now adding variables. First, I'm adding south. That's a characteristic of the restaurant. Then I'm adding south and burger, also a characteristic of the restaurant. And let's first see what happens then. So I'm adding south here. That's a good predictor. Significant. And now we see the row that we had of 10% has decreased to 9, loosely speaking. So apparently from the 10% that we had at the cluster level, now we have taken away a bit and rows going down. Now I'm adding burger, another characteristic of a restaurant, also works well. Burger restaurants on average score lower. And my row is decreasing even more. As long as I keep doing this, adding restaurant characteristics that work, that row value will keep going down. Now add something that is a characteristic of an employee, and we'll see that our row is now increased back up again to 10%, which in principle makes sense, or can make sense. Male is indeed here working. Males give higher grades to their manager than females do, apparently. So now we have taken away a part of the individual variance, and the part that resides from the variance that is left over, there is now a larger part again at the restaurant level. All right. Then, just to show you that it's in principle possible, even though you get a big mess, is now I'm adding all predictor variables that I have, as I did before. I do not take into account any multi-level stuff. I simply add all the dummies. One of the things that you now get is typically something like this. Some of these dummies are not working anymore because you have explained away too much other variance with these other predictor variables already. So this already doesn't look very convenient here. We still have 145 of these things being estimated, yada, 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 and only the variables here that we are really interested in are still there, but sort of hidden in a big layer of 145 estimates. Also, what you see now, many of these are now not significant anymore. So that is, in a way, a bit worrisome. When we ran the regression originally, without the dummies here and without the multi-level, quite a few of these were actually significant. And now, when I control for these separate restaurant dummies, quite a few aren't anymore. So let's see what happens if we do this, let's say, the right way. Okay, now first, just for comparison's sake, I add my standard regression here. Then I define the cluster level through xt set restaurant, and then I do the same regression as I had before, but now with the multi-level option included. There we have it. Doesn't look so bad. Let's see, this was the standard regression. This one's not significant. Burger and years on the job also not, the rest is. Now let's see here, this one's not significant. and that one also, and well, this one is close perhaps. So here, apparently that 10% of variance at the cluster level doesn't do that much damage in the sense that my estimates change a lot. But nevertheless, I'm now still taking into account that there is clustering in the data, and there is only, well, close to 0 left at the cluster level at this point. So apparently, from the variance that is left over, not a lot of that resides at the restaurant level anymore, which is a good thing. In principle, if you have this, you know, really 0, you could argue here, it would be just as good to run a standard regression. Okay, now the splitting part. This is slightly more complicated. For all the lower level variables that I have, I can do the splitting exercise here. So for instance, for age, what I create is 2 variables based on the single one that I had. So I had the age of the employee. And what I create is, well, I call it m underscore age. That is the mean of age across a restaurant. Okay, so I look at all the employees in a single restaurant and I calculate their mean age. You do it like this. Buys restaurant. Yeah, and then eGen stands for extensions to generate the mean age defined like this. And I create another one. D underscore age. Typically, I stick to m underscore and d underscore, but if you want something else, that's fine too. And that is the difference of age with that mean. And these 2 variables, m underscore age and d underscore age, allow me to split the potential effect of age in an effect of age within a restaurant and an effect of age across different restaurants. So perhaps it's a good idea to first, let's see, take this one. And only do that age variable. So instead of age, I now add m underscore and d underscore, splitting that age variable in 2. And there we have it, right there. So now we see 2 things. In fact, in this case, it doesn't matter so much because both of these effects are negative, minus 0.1 and minus 0.14. But you see evidence for both effects here. First, let's look at the d underscore age. That is the effect at the individual level within a restaurant. The ones who are older give lower grades. And that one is the effect that runs over the means of age. Restaurants with older employees get lower ratings. Okay? Anybody not in sync with that? Because this will do now for all the other ones as well. We have years on the job, which is a characteristic of a person. We have male, which is a characteristic of a person. And let's see. There we have it. We include all of these. So I do away with the original ones and get all these m underscore and d underscore variables. And let's see where we do find a difference. Well, yeah, there for complaint. We have d underscore complaint and m underscore complaint. Complaint is a dummy variable consisting only of whether or not, yes or no, a employee has filed a complaint at some point with the manager before. And this is saying, okay, if you are somebody in a restaurant who has filed a complaint, you are at some point ever before, you are more likely to give a higher grade, which is sort of weird, to your restaurant manager. And that one is saying, in restaurants where more complaints have been given, the grade is lower. Now, you see here that in this case, only this one is the weird one that we don't really understand. Perhaps as soon as you file the complaint, you know, you make good at some point and things get better and now you like the manager more. This one is not significant, in fact. So this would be a slightly downward sloping, but in principle, horizontal line. So this is one example where you see happening that the effect in one direction need not be the same for the m underscore and the d underscore. For these, you see that none of this is actually working. For male, you see that the effects are again in the same direction. This one, the d underscore, is saying, okay, within a restaurant, males give higher ratings, and across restaurants, restaurants with a lot of males in it, also get higher ratings. Okay. All right. Now for the $1,000,000 question. I did this for these variables over there. Okay, why not, for instance, that one or that one? Who knows? It wouldn't work. Why wouldn't that work?
I think because those are at the restaurant level, and the ones
Mhm.
you changed are all at the individual level.
Yeah, but why is it a bad thing that they are at the restaurant level?
What do you mean?
Well, you're rightly saying, yeah, this is because all the other ones are at the restaurant level, but yeah, so what? Could do it. What would go wrong? No clue. Try to think mentally what would happen. First, I calculate across all restaurants the mean of a restaurant characteristic. Well, I can do that. So if I have some mean, I don't know, 6.5 for a restaurant, that 6.5 is there for all the cases for that restaurant. So the thing is going to be 6.5. Okay, no trouble whatsoever. But then I'm going to calculate the difference of the original variable with that mean in the restaurant. If I have something that is constant within that restaurant, it's 6.5 all the time. The difference from the mean is 0. So for the difference from the mean, I get all zeros. I can create my m underscore variable, and I also can create my d underscore variable. But my d underscore variable will be 0 everywhere, and that doesn't help us much. So everything that is at the restaurant level cannot be split in something at the restaurant and something at the individual level, because at the individual level there is no variance. It's a restaurant characteristic. Doesn't work. Okay. Now let's see if I want to continue with this part or do something else here. No, this part I'll skip for now. So let's get back to what we had here. Where was I? Okay, so now the hope is that given that I've shown already how this works in Stata, now this is more obvious, because this is basically stating just formula-wise what I just did. So I have here y dependent on x1, and what I create is two variables, the mean of x1 per cluster or per group, and the deviation from the mean within the group, and I add both as predictors instead of x1. Which is a good thing, because instead of the single thing that I could test, I can now test two different things, and really substantially different things. This is what we just saw in Stata. I did the demo already. So we have xt set and xt regress, and what we need to do is something like this. Bias restaurant, we had extension to generate m underscore h equal to the mean of h, and well, the underscore h, I call it, equal to h minus the mean of h. Nothing new. Let's see, what can be split up? Well, it has to be at the lowest level. Otherwise, you can split it up, but if you add them both, it won't work. So if you forget which one you can split, just try, and you'll see that it won't work for one of these. And these are, in principle, for the, let's say, for the first part, the standard solutions to two of the issues that we have here. First, you need multi-level because there's clustering in the data. Well, easy. Do that xt set and xt regress. And for the rest, there's basically not much new. And we have within and between cluster effects also dealt with. You do this procedure with the means per cluster and the deviations from the mean per cluster, and you're good to go. Now you have two separate effects that you can test, even though you have just a single variable. Okay, that was the easy part. Well, easy part. First part. Worse has yet to come. Okay, so all the stuff that you do not understand at this point, tell me now. Otherwise, you get more lost in the next bit. Anybody who stumbled over the analyses that we just ran in Stata? Because in principle, if you can read a regression table, you can also read this table over there. As long as you know how these by commands work, it should be fine. Everybody okay? All right, here we go. Now, the boring assumption checking bit, don't want to go into that in too much detail. But an obvious next question would be, what if you would have more than 2 nested levels? We could have not just pupils within classes, but pupils within classes, classes within schools, schools within big bunches of schools within provinces, and provinces within the Netherlands. So you have way more nested levels than just 2. I must admit that in actual data, that much is relatively rare, but 3 could easily happen. What do we do then? And, what's even worse, we will see, but that we will only see next week. What if we have 2 levels, but they are not nested? If we have pupils within classes within schools, these are nicely nested, fine. But if we have, let's say, pupils within classes, and at the same time pupils within sports clubs, where there is no need that both are nested within each other, then you have to do something else. And one that you will see most often, that's the last one. We had these kind of things, where we saw, for different kinds of classes, we could have different kinds of intercepts. But this is assuming that they all have pretty much the same intercept. And why would they? Might very well be that the intercept is, let's say, on average positive, but a bit more positive for one, and a bit less positive for the next one, and so on. So we have, differing slopes also, and not only differing intercepts right here. And for that, we need to do something else. And in fact, the whole command then changes, because that xt set and xt reg will only work if we do what we just did. And if we do something more complicated or need something more complicated here, then we need a Stata command that's called mixed. And that mixed uses a slightly different interface than the xt commands. In fact, actually, the whole bunch of xt commands is now obsolete. I think it was left behind in, Stata 12 or so, and we're now at 14. But it still works, and I think for the initial analyses, this is way easier than that mixed command that we'll see in a minute. Okay, I can't say this too often, so I'll do it again. It does take some practice. You do this a couple times, and at some point you start to feel, this is how it works, apparently. Okay, so first, let's get the assumption checking out of the way. So what did we have here? This I already mentioned. This is your standard regression model, now for ease of exposition, just with a single predictor, 1x1. Nothing fancy going on. I think that the data are clustered in this example, and what I'm assuming is, actually what I'd like to do is include dummies for each and every one of the clusters that I have. But because I have so many, what I'd like to do even more is summarize these dummies in one letter, basically, called delta. And what I'm assuming is that delta thing there is normally distributed as a zero mean and a variance that I will estimate. That estimated variance will give me that rho, but that normally distributed, in principle, actually I would need to test this if this is really working out. And we can, and it would be really, really nice if there was a standard command for it, and there isn't. So we have to figure out how to do this ourselves. I'm not sure what I wanted to show here, but this is where you can see that these intercepts would be lying there, right, on the y-axis. That would give me a big bunch of different numbers. From that big bunch of different numbers, I could try to make a graph. I would hope that it looks like that, and then estimate whether or not that distribution is normal, yes or no. Let's see. Do I have that here? Yeah, we have it. Okay, so here you see the same thing in words. The whole thing is only allowed when these different dummies actually would follow a normal distribution. And there's a bit of a paradox here. So actually what I want to do is multi-level regression because it's way easier and I'm not dealing with all those dummies. I can only do this if the distribution of these dummies is such that it is normal. But if I can assess that they are normal, then apparently I could actually estimate that model with all the dummies to begin with, and I wouldn't need multi-level. So it's a bit weird, a bit of hand waving involved here. But nevertheless, we can give this a try. You run your model first with all the dummies included, as we did it, one dummy for each and every one of the restaurant, and then check for the coefficients of these dummies whether or not they follow a normal distribution. You need a bit of code for that. Looks like this. This is something you have to get familiar with, and it's useful to know a little bit about these different kind of things. Let's see, this is my standard regression here. Regress y, and then D2 through D40, that's my dummies that I have there, and I have other predictor variables, let's say x1 and x2, doesn't matter so much. Now I get a regression table, and now I'm going to create a variable, a new variable in my data, and what I'm going to store in that new variable are the estimates for these separate dummies. So I get an estimate B2 here, an estimate B3, all the way up to B40, and that number that you would find in that output table, I'm going to put in a variable. That's the idea. And this is the way to do it. First, I create a new variable called coef, or coefficient, equal to missing. This gives me an extra variable in my data with nothing in it, just labeled coef. That's it. Now I run a for loop, running from 2 to 40, the 2 and the 40 coming from this 2 and that 40 over there. Curly bracket over there at the end of the line, curly bracket over there at the last line, and you have to do it like this, otherwise it won't run. Okay, now what I do, first I have to tell Stata what the counter in this case is, it's an I. And now the complicated part starts. What I do here is first, okay, I replace the coefficient variable with, well, with what? Underscore b and then square brackets. What does that mean? Underscore b and then the square brackets stands for, give me the estimated coefficient for the variable that's between the brackets. For instance, what I would like to have is the coefficient that was estimated for D2. And when I enter the for loop here, y will be 2 first. I can call the y, I can call the thing that I've labeled over there with a single accent in that direction, and then a single accent in the other direction, and it really has to be like this, so no double ones and no two the same single ones, one left, one right, otherwise it doesn't work. So this is now parsing out D2. So actually this says, the first time that you get into the for loop, replace coef equal to underscore b square brackets D2. Give me the coefficient of D2 and replace it, but only if the line number, that's underscore n, equals 2. So now what I get back is in row 2 of the variable coef, I get the estimate for the dummy D2. And that I do, same thing for D3, D4, D5, all the way up to D40. And what this will get me is a new variable in my data labeled coef with nothing in the first row and exactly the estimated coefficients for the dummies in rows 2 through 40. And nothing behind that. Everybody okay with that? Just a bit of code. This one is, if you are very into it, has to all be on a single line and you can remember it. In fact, this is also sort of lost code. This is not officially supported anymore, even though it still works, but you could do it in a single line of code if you wanted to. And then what you do is, okay, given that I now have that coef values, coef variable with all the values in it, I can check if it's normal. And if it is, great. If it's not, then actually I wasn't allowed to do the analysis in the first place. Let's see if I have a... do I have that? No. Okay, so I'll show you in a minute how that goes on the actual example. Let's see, because there is another way to do it. This is the slightly different way to do it. This is using the xt set of commands. So first you define your cluster level variables. Here I labeled them ID, but in our data this is called restaurant. And then I estimate my multi-level regression twice, once with the option fixed effect and once with the option random effect. Okay, actually what's going on behind the scenes here is that here, this is, well, sort of similar to having these dummies, but not completely. And this is sort of, no, this is in fact exactly similar to not having this option here. So random effects is the default. I just add them to make sure visually that you see that there is a difference. This is one way to do it with all the dummies included. This is another way to do it. And I store both. Estimate store, and I call them fixed. Estimate store, and I call them random. And then I do a comparison of these estimates. And this is actually doing something that is slightly different. This is doing, if I run my analysis with my predictor variables and then all the dummies, and I run it as multi-level with the predictor variables and then that row value over there, basically what I'm interested in is, does it matter very much for these two sets of coefficients? If these are more or less the same, I would be fine. Then apparently using all the dummies or using that delta and epsilon is not doing any harm to my estimated coefficients, and that is good enough. So we do not focus on the normality so much anymore. The thing that we look for is, okay, the coefficients that I estimate, as long as these do not change very much from one to the next, I'm fine. And that's called the Houseman test. And then you compare the estimates. So let's see how that works when you do it in Stata. There you have it. Here you see that you do need a little bit of extra work here to get this going, because I saw that, well, there are 145 restaurants in there. And first I create separate dummy variables by hand, so to speak, through this tab restaurant, generate R. This will give me R1, R2, R3, and so on, all the way up to R145, dummies for the separate restaurants. And now I run this thing as you saw it on the slide already. Let's see, generate, I call it, not sure why, not coef, but coefficient underscore R, first equal to dot. I put the value of 0 in the first line. That's actually a bit more correct than what I mentioned. In the example, I left the first line empty. That's for the dummy that you do not have in the actual regression. But by definition, that coefficient is 0, so I added the 0 there. And here you have that for loop. Let this whole thing loop from I equal to 2 all the way up to 145. Replace the coefficient with the estimated coefficient, and I test for normality. Let's hope that that runs. Did it stop earlier? It did. Okay, so let's see what we get. Here we get our for loop. Here I estimated that whole thing with all the dummies involved, 145 of them. See, regression, all the dummies included, yada, 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 yada. I'm creating a new variable here, coef. I replace the first line with a 0. And now you get for each and every one of these from 2 to 145, I replace the coefficient. One change made, another one, another one, another one, all the way up to 144 changes. I'm testing here for normality, and yes, normality is not rejected, which is a good thing. So I'm good to go. Questions about this part? Easy? All right, yep.
Can you just use restaurant 1 instead of R1 and just don't generate that R?
How do you want to do that?
I don't know, you generate a variable called R,
there.
Yeah, over there.
Yeah.
You can just use restaurant 1 till restaurant.
No, I mean, I have at this point, before executing this command, I have the variable restaurant in my data, just restaurant, and it is equal to 1, to 2, to 3, and so on. But I do not have a variable restaurant 1 or restaurant 2. So if you want it to be called like that, that would be fine with me. Then you simply have to type this. That'll also work. Now you'll get restaurant 1, restaurant 2, and so on. So you can type whatever you like for the new name. But it doesn't do this automatically. And the other way to do it here for this regression would be regress grade I dot restaurant. But then this should be different as well. I find this one a bit more convenient. Any other questions about this part? Just some coding. And here the same procedure, but now with that Houseman test. I'll add some air to the code so that you can see better here first. Okay, define what the cluster level is, then run it with fixed effects and store it, run it with random effects and store it, and do the actual testing. Oh, like this. Okay, there we go. Estimates for fix. Where are we? There we have it. So first I define my restaurant variable. I'm looking at fixed effects here, and that means all the variables here at the restaurant level are in this case not included anymore. The rest is age, complaint, years on the job, and mail. I store them somewhere. I run my standard multi-level. This we've seen before. And now I do my Houseman test. This is the set of estimates that I got for age, complaint, years on the job, and mail when I ran the fixed effects. This is where I get the random effects. And I'm testing now whether these two columns could be the same here, or whether or not I should reject that they are the same. And I want that they are the same. And this is actually rejected. So here, this is one of these nasty examples where when I try it one way with these dummies and then to check if they are normal, okay, that worked because it was normal. When I try it the other way, then I get, actually here, what we see is if I run multi-level, assuming that delta in there next to that epsilon, then I get something that is different for the coefficients at the individual level, which is not what you want. So this would be suggestive of, well, if you do it like this, with these variables included, then actually multi-level is not working well here. What could still happen is if I split these in m underscore h and d underscore h and so on, or if I add a couple more variables, then perhaps this test is okay. But if you look at it like this, now you see that the H0 hypothesis is rejected, and you shouldn't have done the multi-level regression in the first place. Which also implies that it can happen that you cannot analyze the data in the right way. Normal regression would not be right, because you see that the data are clustered. Including all the dummies might be problematic, because you have so many. And running multi-level might not work, because the assumptions are not fulfilled. And then in the end, the only thing you can do is put your hands in the air and surrender, because there's nothing else to do here. It's actually not completely true. You can do more complicated stuff, but given that we are up to here, there's nothing more you can do. Let's see. Yes, all right. Back to the PowerPoint. I had some examples here as well that we can now skip. Yeah, and here another one of these examples where apparently H0 is rejected and we're screwed. This is not working. Also, this is, a very important point actually. This is one of the cases where, and this may happen more often, I've seen many papers where the checking part is sort of forgotten or implicit. So you're supposed to assume that the one who wrote the paper has done this and all this was okay. But for quite a few of these, well, perhaps they do not know that they actually have to check this, or they do know and have checked but didn't want to report that it actually didn't work out. So here actually knowing more or knowing better what to do might be hurtful, in the sense that if you are honest, as you should be, And if you are knowledgeable, as you should be, then you might end up in a place where you have to decide, okay, I see here, I cannot estimate this, and that's it, and you shouldn't report it. And I must admit that there must be way more people out there, actual researchers, even the ones that I normally highly value, who simply do not check and just present the model and then hope that all has been okay. Okay. Then, other assumption checking we can be relatively short about, well, at least as long as we assume that you more or less know what we did before, because all the standard assumptions that were there for standard regression are still there for multi-level regression. And the complicated part of it is that many of the standard tests that we had before, after regression, do no longer work if you type XT-reg. Would have been nice that they would, but they don't. And the higgledy-piggledy way to solve this is, okay, if we want to test for this, we simply forget for a minute that this is actually multi-level data and just run our tests as if we would run them on standard regression data. So for homoscedasticity, we had a command that was called head test. And well, maybe it's changed in version 14, but I don't think so actually. So after XT-reg, your head test command will not work. And the only way to get around it is, okay, forget that for a minute and just run regress and then type your head test. Then it will work again, of course. Normality of the residuals, linearity, all that stuff, that's all old, or should be all old news. And if it doesn't work, the particular command that we had there, use the old one on standard regression. And one way to make you feel better about doing this is if that row value that you have is close to 0 anyhow, then it's not so bad, because this is saying, okay, just using regression instead of multi-level regression is more or less the same thing. So then the issue is not so big. If you have row values of, let's say, 0.6 or 0.7, which would be really high, then testing like this would be actually, really weird. But given that it's the only thing that we can do here, we sort of stick to it. Okay. Yeah, then the good news, or good, would be that as soon as you know how that XT regression works, and as soon as you know how logistic regression works, you also know how multi-level logistic regression works, because the only thing that's different is that the XT is now coming in front of the logit command. That's the only difference. The rest is the same, with one minor exception. I have to peek if that's here. Yeah. Here I'm running an XT logit on the variable that was also in the restaurant data. I took complaint, just because that one is 0,1, not because I'm so interested in it. You get something, well, that's different there. You get two sets of iteration logs. So in a way you get two ways in which the whole iterative process can get stuck. Usually it doesn't, but it can happen. And what you get here is also slightly different. In the other command we had a sigma e and a sigma u, and that would give us a row. Because this is logistic regression, sigma e and sigma u are not well defined. You can fix one, usually it's fixed to 1, and then calculate the other. So this is not something weird going on, this is normal. For any XT logit command you will not see that sigma e anymore. It's fit to the, I think to 1, I'm actually not completely sure, but I think it's fit to 1. And then that row value is again there as you would want it, and in fact usually this is typically the thing that you're looking at, that row value. So in this case about 6% of the variance lies at the cluster level, at the restaurant level here. Okay, I won't go into the details of that XT logit in any amount of detail, because in principle this is largely the same. Although the same nasty issues that go for regression also hold here, there are commands that work after logit, but do not work after XT logit, and then the only thing to do would be just, okay, let's forget for a minute that it's multi-level and just do it. All right, let's stop at this point. Any questions that I need to answer today? If it's something that you prefer asking in private because it's related to any wiki stuff or material, I'll stay here for a couple more minutes, but after that I have to leave, I have to teach somewhere else. So otherwise, I'll see you next week.